Well, as we get started with Chapter 18's exercises, we can look at what we call Electron Dot Notation and then use that to help us figure out how to do covalent bonding and ionic bonding using Electron Dot Notation. First, I want you to pay attention to this Q right here with the 8 numbers around it. That's important for a reason, because let's start with the element helium, or neon rather, not helium, because neon has 8 valence electrons. Just follow the pattern that you see over to the left on the Q. And since we're talking about dot notation and all we care about are the valence electrons, that's pretty cool. Neon, argon, krypton, xenon, and radon, all noble gases, are all going to work exactly the same way. All right, so let me get rid of this and make it a little more room. And then let's do the dot notation for neon. All I have to do is put the first dot here, second one here, like you see on the left. Third one goes here. There's 4, 5. Keep on going around and you'll fill in the other spots. 6, 7, and 8. And if we do this correctly, we really wouldn't be able to tell the exact order that you put them in just by looking. But you see, if I draw well, it looks kind of like a stop sign. All right, so now again, compare the neon we just finished with the Q pattern over to the left. Let's clear this off, and we'll go ahead and get started. As I scroll down to the first, I don't want to go too far, to the first 4 that we have. Our first element given is calcium. So find calcium. It's element number 20. It's in group 2A, so it has 2 valence electrons. Just follow the Q pattern. So 1 and 2. Next one over to the right, AS, is element number 33. That is arsenic. And arsenic has 5 valence electrons. 1, 2, 3, 4, and 5. Oh, that one didn't draw the first time, so there you go. Next one is gallium, which is in group 3A, so 3 valence electrons. All I have to do is 1, 2, 3. Silicon is in group 4A, so 1, 2, 3, 4. And I'm going to pause here, and I'm going to give you a chance to try the next 4, and then I'll put all the answers up there at one time. So I'm going to go ahead and pause while you do that. All right, hopefully you've had a chance to try it, and here you see the answers. Potassium, group 1A, 1 valence electron. Argon's a noble gas, group 8A, so it gets all 8 of its electrons. Iodine's a halogen, group 7A, so only 7 of those. And selenium, element number 34, that's in group 6A. So really that's all there is to it if you're doing the dot notation for just a single atom. It gets a little more complicated when we do the covalent bonding, as you're about to see. All right, so I'm going to clear off the screen here, scroll on down to the first covalent bond, and we're going to see that it is diatomic hydrogen. Now remember, hydrogen is diatomic. That means you will never see a single hydrogen atom by itself. Remember, it's one of those 7 that I want you to memorize, and we talked about those in the covalent bond notes, 18A and B. Hydrogen is diatomic, and here's how those come together. So first, I'm going to change over here to the purple. Now, notice that I like to use the different colors for these, so hopefully you'll see what's going on and how these things come together. All right, since hydrogen has only 1 electron, that means it has only 1 valence electron. So I'm going to start with purple. So all I'm going to do is sharing means stick the electron in between so both can use it. All right, now let's look at the green hydrogen atom as I change colors to green. And I put that one in here. And there you see that each hydrogen atom, remember, hydrogen has only the first energy level, so it's filled up with 2 electrons. It's not trying to get up to 8. But now here's what I'm going to do. I'm going to erase those and kind of talk through it this time. Starting again with the purple one. So switch back to purple. And then kind of talk through it this way. Well, each hydrogen atom has 1 valence electron and needs to use 1 more, and they're very generous. The atoms really like to share. So the hydrogen on the left, the purple one, is saying, you know what? I have one valence electron, I need one more, and you're in the same situation. So let's do this. I'll take my one valence electron and I'll stick it in the middle, and now we can both use it. And then the green hydrogen atom says, you know what, that's a pretty good idea. So I'll take my one electron, put it in the middle, and we can both use it. Now look at this carefully. What we have now is we have a pair of shared electrons right there that goes with each hydrogen atom, and this one is finished. That's all you have to do for the hydrogen. That is absolutely it. This one hydrogen atom will get to use both of those valence electrons, and this second hydrogen atom will also get to use both of those valence electrons. Since hydrogen is happy with just one valence electron, this one is finished. So let's clear that off. And then we'll move on to the next one. Next one is diatomic oxygen. All right, so we're going to use brown and red. But before we do, I'm going to go ahead and redo the hydrogen very quickly so you can keep looking at that as we look at the diatomic oxygen. So let me switch to brown. Because here's diatomic oxygen. Find oxygen, element number 8, group 6A. It has 6 valence electrons, so how many more does it need? It needs 2, and so does the red one. So each one is going to say the same thing. Well, you need 2 more, so here's what I'm going to do on the brown. I'm going to share my 2, and I have 4 left because I have a total of 6 valence electrons. But since I'm not sharing those, I'm going to keep those to the outside. And then the red one does the exact same thing. Okay, then I'll share 2 with you, and I'll keep my other 4 on the outside. So what's going on now is, if you look carefully, switch colors so you can see this, you look at the oxygen on the left, the brown one, it now uses its own 6 plus the other 2 from the red oxygen, and now that oxygen atom is using all 8 of its valence electrons. Well, so is the orange one, or the red one, doing the same thing, using its 6 plus the other 2 from the other oxygen atom. So now this oxygen atom now has 8 valence electrons. By sharing, they're both happy. They're both stable on their outside energy level. And that's very much like the hydrogens up above that need only 2 valence electrons to fill up their one and only outer shell. So let's clear this off. If I hit the correct button, there we go. And we'll scroll on down to the diatomic nitrogen, which might look a little bit tricky, but not as much as you think. All you have to do is count to 8. All right, so I'll start with the orange one. Nitrogen has 5 valence electrons, so it needs to borrow 3 more. So each nitrogen atom is going to do this. Well, since you need 3, I'll put 3 in the middle that we can share, and I'll keep my other 2 on the outside. So once you get used to this, you'll see it's really a lot easier than it looks at first. And then the second nitrogen atom says, okay, then I'll do the same thing. You need 3 from me, so I'll share my 3, and I'll keep my other 2 to the outside. And once again, what we have here, 2 stable, happy nitrogen atoms, because each one is going to use its own 5 plus the 3 from the other, and now that nitrogen atom has 8 valence electrons. And same with the other one. Its own 5 plus 3 borrowed, and that's a total of 8. So this sharing in between allows each nitrogen atom to use 3 valence electrons of its own, plus get the other 3 from the other atom, with the 2 that it has by itself on the outside. So both nitrogen atoms, because of covalent bonding, sharing electrons, both now have 8 valence electrons. All right, let's go to the chlorine. I have to scroll down a little bit to fit it on the screen. All right, so we have chlorine now. So I'll switch to purple because you see the purple. I hope the colors are helping you see each electron from the atom that it came from and is going to be shared. All right, so chlorine, find that one, element number 17, group 7A. It is a halogen. Since chlorine has 7 valence electrons, it has to share how many to make 8? 1 more. So just like the other atoms did above, chlorine is going to say, how many do you need from me? That's how many I'll share. So the one on the left in purple says, I will share 1 with you and keep my other 6 out here to myself. And look what the green one will do. Green one's going to do the same thing. Okay, I'll share 1 with you, and I'll keep the other 6 out here also. And once again, this time I won't draw a box around it. I'll do it this way. You can see that each chlorine atom, because of the sharing, is now going to use 8 valence electrons. So those are the diatomics. Now with the halogens, since 4 halogens are diatomic, we could have actually used fluorine in there, or bromine, or even iodine, because they would have done exactly the same thing that chlorine does. But it's not only diatomic molecules that use covalent bonding. Here's a formula you're very familiar with. Water is H2O, so I'm looking at the 2 brown H's and the red. But the concept is still the same. Each one's going to share what the other atom needs. Well, hydrogen, remember, has exactly 1 valence electron, so that's all it can do. Well, I'll share mine with you, but each one is going to do that. Now, oxygen has 6 valence electrons, and really I could have started with oxygen if I wanted to. But I started with hydrogen. Doesn't matter as long as you do them both. Oxygen has a total of 6 valence electrons and needs 2 more. Well, look, that red oxygen just took an electron from each hydrogen, and it's going to share with hydrogen to give hydrogen the 2 that it needs, and it's going to do it on both sides. Atoms share, and they share evenly with everybody as much as possible. Now, oxygen has 6 valence. It just used up 2 of those, so that means it has 4 left to keep on the outside, and now we're finished with the water molecule. And that's really all there is to it. It looks more complicated than that, but it isn't. Right, so I need to clear this off so I can scroll down a little more, but I'll pause it for a moment. I'll let you pause the video for a moment so you can see what happened there. Okay, let's scroll down to a compound that we call methane. 1 atom of carbon and 4 atoms of hydrogen. All right, this time I'll start with the carbon since I started with the hydrogen last time. It really doesn't matter, okay? Carbon in red. Find carbon, element number 6, group 4A. Now remember, carbon will share all 4 because the 4 it has plus 4 more it needs is going to make 8. And the atoms like to do it generously and evenly. So carbon's going to say, okay, I have 4, you each need 1, and I need 1 from each of you. So here's 1 for you, here's 1 for you, here's 1 for you, and here's 1 for you. Make that one a little bigger. And hydrogen is going to do the same thing. So I'll switch over to blue, and hydrogen will say, well, I'll share my 1 with you, and each hydrogen will do that. I'll share my 1 with you. Now, let's look very carefully. Each hydrogen atom has 2 valence electrons that it needs. And we see that in 4 different places. But now the carbon that started with 4 because of sharing now has 4 plus 4 from the hydrogens for a total of 8 valence electrons. And that is how methane uses 1 carbon and 4 hydrogens covalently to get a formula of CH4. All right, look at that for a moment. Pause it here before you move on. All right, let's scroll down some more and see how ammonia works. Do you think it'll be the same or different? It's going to do very much the same thing. All right. Usually I will start with the hydrogen, so I'll go ahead and do that this time. Hydrogen in green. All right, so hydrogen with 1 valence electron You might have noticed that I had 3 N's and 1 H, and I paused to change it to get it correct, because ammonia is NH3, so 1 nitrogen and 3 hydrogens. So we'll go ahead and we'll start with the hydrogen. Like I said, I usually start with the hydrogen. Each one can give 1 valence electron, so here you go. And the one on the bottom says, here you go. And the one on the right says, here you go. And now we look at the nitrogen with 5 valence, and we'll share 3. And it's going to spread those 3 around evenly. So 1 for you hydrogen, and 1 for you hydrogen, and then I have 2 more to keep all to myself. And once again, look at the final product. Each hydrogen atom has the 2 valence now that it wants, 2 there and 2 there, and the nitrogen has 2, 4, 6, 8 valence electrons, so we get a very happy ammonia covalent bond molecule, NH3. Pretty cool, huh? Well, that's 2 nonmetals that will do covalent bonding, but ionic bonding, I want to make sure you can see the word up there, that's always going to happen between a metal and a nonmetal. I had a little bit of a lag, but now you can see on the screen there, ionic bonding. Well, what we're going to do with ionic bond is we're going to have 2 parts. So the left side is before, and the right side is going to be after. Okay? So let's look at each one's valence electrons once again. Well, sodium, group 1A, 1 valence electron, right there. Fluorine is a halogen, group 7A, so 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Now, when the atoms start to bond, they don't necessarily follow that Q pattern I showed you earlier. They're going to move around and make room for the one that's trying to move in. Well, remember, the metals love to give away their valence electrons. The nonmetals love to take those. So sodium's going to kick that 1 electron out, and it's simply going to move into that 1 opening there on the fluorine atom. Now, because sodium has given away that 1 valence electron, it now has still 11 protons, but now only 10 electrons. So add those 2 together, plus 11, negative 10, that's positive 1. That's why you see the plus 1 up there. But since we're talking about the valence electrons, sodium doesn't have any more, so I'm not going to draw any dots around the sodium on the right side. But I will for fluorine, because fluorine just took 1, 2, oh man, that's bad. Let me erase those and try again. 1, 2, 3, 4, 5, 6, 7, plus that 1 electron it just took from sodium, and now it has all 8 valence electrons. But now fluorine, that started with 9 electrons total, now has 10. That means it has a negative 1 charge. And it's these opposite charges that stick together. Remember, electrostatic forces, that holds ionic bonds together. And it's a very difficult bond for ionic bonds, and very difficult to break those apart. So those are going to stay together quite a bit. Now let's clear this off, move down to the next one. Calcium oxide. Calcium is in group 2A. It is an alkaline earth metal. So let's get its 2 electrons. 1, 2. Oxygen is in the oxygen family. It is group 6A. So 1, 2, 3, 4, 5, and 6. Well, remember, we're trying to get a total of 8. Oh, that was bad. I'm trying to put that one right there. Okay. Trying to get a total of 8 valence electrons. Well, calcium has 2 to give away, and oxygen has 6 and needs 2 more. So this is a perfect 1-to-1 matchup. So see what happens here. The electrons from the calcium atom, this one says, hey, I'm going to move right into that opening there, and I'm going to move into that opening right there. Since calcium just gave away both of its valence electrons and now has a positive 2 charge. Remember, losers become positive. And with the oxygen atom, the 6 that it had, 1, if I can get it to draw, 1, 2, there we go, 3, 4, 5, 6, plus the 2 that it just took on. Man, I can't draw. Let me try that one more time. 1, 2, 3, 4, 5, 6, plus the 2 that it just took on, gives 8 valence electrons to that oxygen atom. And what is plus 2 and minus 2? Plus 2 and minus 2 equals 0. And that's how you can tell if you did it right. If the charges total 0, you probably did it right. If they don't, you made a mistake somewhere. So both the sodium fluoride and the calcium oxide gave us perfect 1-to-1 matchups. That doesn't always happen that way. Look at the next one, lithium sulfide. You notice that lithium has a little bitty 2 because it takes 2 lithiums to pair up and match up with 1 sulfur atom, and you're about to see why. Find lithium. It is element number 3. It is an alkali metal. It has 1 valence electron. That's why it is in group 1A. So just that right there. And since there are 2 of those, well, I'll wait a moment before I put it up there. Hopefully you'll see why after I do the sulfur. Because sulfur is in group 6A, which means it has 6 valence electrons. That's the reason it's in 6A. So 1, 2, 3, 4, 5, 6. So now let's go back to the lithium atom. Well, the lithium can move that electron into the one opening, but sulfur still has another opening. How's it going to get that 8th electron? It now has 7 because it took 1 away from the lithium. That's why we need a second lithium atom with its valence electron to move into that last opening right there. So now that lithium, each one has given away its 1 valence electron. Each lithium will now have a positive 1 charge. That's supposed to be a positive 1, but you know I can't draw. Now, what about the sulfur atom? Remember, it started with 6 valence electrons. 1, 2, 3, 4, 5, 6. But then it took 1 from the first lithium to make 7, and 1 from the second lithium to make 8. And now, since that single sulfur atom just took on 2 electrons, it has a negative 2 charge. So let's do the math. Plus 1, and negative 2 all equals 0. I know I did this right because I got 0, and it's the only time I want you to get a 0 in this class. But you look carefully and you see why it takes 2 lithium atoms to match 1 sulfur atom to give us a complete lithium sulfide molecule. All right, one more, calcium chloride. Calcium is group 2A. It's an alkaline earth metal, so 2 valence electrons. Chlorine is a halogen, group 7A. It has 7 valence electrons. And yes, I have to do it on both. I know it gets tedious, but that's the rules. That's the way we do it. So now, what happens with each electron from the 1 calcium atom? Well, chlorine has 7 and will take 1 from the calcium atom. Now chlorine will have 8, but what about that second calcium electron? That's why we need a second chlorine atom. That second chlorine atom will take the other electron, and now each chlorine atom is going to use 8 valence electrons. I just wanted to show you that for a moment, and now let's fill it in. I had to clear the screen and make a correction, but now, because that chlorine atom just took the electron from the calcium, that first chlorine now has all 8 valence electrons. Because remember, that one went into the opening that was there, and the second one went into the opening on the bottom chlorine atom. So that second chlorine atom now also has all 8 of its valence electrons. All right, calcium just gave away 2 electrons, so it's +2. The top calcium just took 1 electron, so it's -1, and the same with the other chlorine atom. So we now have a +2, -1, and -1. We get 0, so we know we did this right. All right, I said one more, but there's one here that I'm going to go very quickly to show you that it can get a lot more complicated. There you see aluminum bromide. Now I'm going to breeze through this one very quickly. Aluminum, 3 valence electrons, 1, 2, 3. Bromine is a halogen, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Hey, in chapter 19, I'm going to show you a much faster, easier way to do this, but sorry, you got to do it the long way right now. So let's go back to aluminum, and here we go. That one will go here, that one will go here, that one will go here. So aluminum just gave away 3 valence electrons. It's a +3. Now we got to finish off the bromine. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Each one took 1 electron and has a -1 charge. +3, -1, -1, -1 equals 0. And that is how we do electron dot notation. All right, thanks for paying attention. Hope you learned something. Catch you later.